So we've talked a lot about how to make a field. Let's talk for a minute about how to get rid of a field. Let's look at electrostatic shielding. Okay, so let's think, how would you do it? What would you build if you had to do this? So there's sort of two things come to mind that we've been thinking about. One would be a shell. Let's make an enclosed room, and let's make a shell just of charge. Okay, so let's make a shell of charge. Right, so this is really a three-dimensional shell, and there are charges throughout this region. And they have some charge density rho in this volume of this shell. And the question is, will that keep an electric field out? You could also think about a metallic shell. All right, so I'll kind of hatch mark that to show that it is a conducting shell. It's probably a metal. It doesn't have to be. So will either of these stop an electric field? So let's imagine then that we have some big whopping charge here plus Q. What will the field be inside? Well, E, the electric field will be 0 due to the shell. And that's a Gauss's law problem that you'll probably do in the homework. You can show that the E field inside this thing is 0. All these charges make fields that cancel out. However, the field due to this will happily go in because it's superposition. E inside here will not be 0 due to superposition. Okay, so this is the real answer. It will not be 0. The shell contributes 0. The shell by itself makes 0, but the field lines out here will just go straight through. I mean, they'll bend around because of the presence of the charge, but eventually you will get field lines in here due to big Q, due to this big charge. So a shell of charge does not screen anything, does not shield you from anything. Let's think about how a metal or a conducting shell might be different. Okay? When the conducting shell is neutral, or even if it's charged, E equals 0, again, due to the shell. A shell itself makes no charge, makes no field. The question is, does it shield from an external charge? And now this will. And the reason is it's different. Okay? This is a conductor, which means the charges can move. So even if it's a neutral conductor, the charges, both the positive and negative, can essentially move. So if it's a metal, the electrons are free to come over here and build up and essentially cancel out big Q, or to attract to big Q, and then you have a big Q, positive Q, and essentially a negative Q there. So you'll have a bunch of charge here, and that'll leave some positive charge over here. So what it'll do is it'll warp the field lines. Instead of having them sort of bend around and go through, every field line that approaches the metal surface, we know, outside of a metal, will end perpendicular to the surface. And that basically means the field line is terminating, right? Field lines always start on a charge and they always terminate on a charge. So this metal shell is going to throw up a charge distribution to terminate all of the field lines right on its surface, just like this. That one will come out and probably go right there. One might come out and do like this. And it does that due to the properties we talked about of a conducting object. Basically, these electrons will move until they can't move anymore. They'll move until all these fields are perpendicular to their surface. And once that field line hits perpendicular, it's finished. Therefore, no field lines get in. So it is actually true that inside a metal shell, E really is 0 if it's empty. So this is screening electric fields from the outside from getting in. The one way you get a charge in here is if you put a charge on the inside. Then that will create an electric field, but guess what? The world will be screened from it. If you put a charge inside the shell, it'll make a field, but that field won't get out. All of its field lines will terminate at 90-degree angles on the metal surface. So metals are really good at screening electric fields, both inside and out.